So what is happening now, right? Now, you read example 4.11 first. Then I explain to you what is happening. You read this?
The woman weighs a fish with spring scales attached to the ceiling of an elevator, as shown in figures 4.36 and 4.36b. While the elevator is at rest, she measures a weight of 40 Newton. What weight does the scale read if the elevator accelerates upwards at 2 meters per second square? What does the scale read if the elevator accelerates downward at 2 meters per second square, as in figure 4.36b? If the elevator cable breaks, what does the scale read?
Okay, right. Now the problem is with the fish now. We are starting with the fish. So you, although they draw a woman here, then they draw a scale here. Now, the scale is just to measure the tension. Now, what is actually happening is we look at the fish. So you copy the fish and we put it outside here. What
Okay.
are the forces acting on this fish? The forces acting on this fish, they are number one, the tension in the hook or the rope that tie the fish onto the weighing scale here. And another force is the weight of the fish itself. The weight of the fish itself. So they are actually, although they have the leaf, the woman, that one is outside our consideration. We just consider the fish alone. So if you look at the fish alone, there are two forces acting on the fish. One is the tension acting upwards. Another one is the weight of the fish acting downwards. So only two forces acting. Now, when one force is bigger than the other, then they will pull the fish in either upwards or downwards, right?
Okay.
Okay, so now they say that the lift is actually moving upwards with acceleration, with an acceleration. So I have indicated it over here, right? The fish is, the whole system, right? The whole system is moving upwards with an acceleration of A. Now,
Right.
if that is the case, that means I know that the tension must be bigger than the weight. That's why overall it is moving upwards. So tension is bigger than the weight of the fish. So I'm going to form an equation involving this. So what is the equation? The equation is the net force. So the net force is actually the tension minus the mass, minus the weight of the fish. Okay,
Okay.
because overall they are moving upwards, so the net force is upwards. So this net force is the difference between the tension and the weight of the fish. So this is what is happening when the fish is, the whole system is accelerating upwards. Now, before we look at this, they also tell us something here. While the elevator is at rest, she measures a weight of 40 Newton. So the fish now measures a weight of 40 Newton. So from this 40 Newton, I want to find out what is the mass of the fish, right? Okay, so you look at this calculation here. Okay, this calculation here. When it is not moving, right, that means this external force is zero, the net force is zero, the weight is equals to mg. The weight is equals to mg. And they tell us the weight is 40 newtons. So 40 newtons is equals to the mass times the g. G is the acceleration due to gravity. So from this, we can calculate the mass of the fish, the actual mass of the fish, not the weight of the fish. From the weight of the fish, here, we can calculate the mass. So the mass is actually 40 divided by 9.8. So 40 divided by 9.8, you bring the 9.8 over, so it's divided by 9.8. So the
Okay.
answer, the mass is 4.08 kilogram. Okay, now why I need to find out the mass of the fish, right? Now the reason is, if we look at the next step here. Now earlier on I told you the net force is the tension minus the weight, but if you remember, the net force is actually the mass times the acceleration. The net force is not mg. So if we don't know the mass, the actual mass, the m here, we cannot find out what is the tension, right? So I need to calculate the mass first, right? Because of the net force is ma.
Okay. Mhm.
So we need to know the mass. Okay, now coming back to our equation for this system here, net force is the tension minus the weight. I replace the net force with mass times acceleration, right?
Yep.
Then the mass times acceleration equals to T minus mg. What we are interested in is what does the weighing, what weight does the scale read if the elevator accelerates upwards at 2 meter per second square. So actually they want to know the reading on the scale. The reading on the scale is actually the tension in the string here, tying the fish to the balance. So this is the tension, and this will be the reading on the scale. So we are going to make the tension, the T, the subject of the formula. So net force T minus mg. T is actually mg plus the net force ma. You just move the mg over to the other side. This mg here, right? You move to the other side. So minus mg become plus mg. So the tension is equals to mg plus
Mhm.
ma. What is mg? Mg is the weight of the fish, and it is given to us. How much is it? 40 newtons. 40 newtons. So I replace the mg with 40 newtons. What is the mass times acceleration? Mass we have found out earlier, 4.08. Acceleration, they told us the acceleration is 2 meter per second square. So acceleration, I replace it with 2 meter per second square. So
Okay.
I add up these two, so I know the tension in the weighing scale is 48.1 Newton. Now, in general, if it is moving upwards, right, the tension will be bigger. If it is accelerating upwards, the tension is bigger.
Okay.
It is similar to our normal reaction. You remember there was one time I listed out 6 cases, 3 cases when the leaf is moving upwards, 3 cases when the leaf is moving downwards.
Mhm.
Now, in general, when we are moving upwards with acceleration, because we need to overcome the weight and at the same time produce the acceleration. So the tension or the normal reaction has to be bigger than the weight itself. So it is bigger than the weight itself. The second case, what does the scale read if the elevator accelerate downwards? So downwards, the weight is actually pulling it down, right? So you don't need so much, right? Probably it will be less. Huh? When it's going up, it's more. Going down, probably it will be less. So we're going to look at the case when the the lift or the elevator is moving downwards. Okay, right.
Mhm.
This is the lift, and the whole lift is accelerating downwards with an acceleration of 2 meter per second. 2 meter per second. The acceleration here is actually 2 meter per second. 2 meter per second square, 2 meter per second square. Okay. Okay, right. So now we look at the fish again. Similar to the first case, there are two forces acting on the fish. One is the weight of the fish, mg, and the second one is the tension, which is pulling the fish upwards. And this also will be the reading on the scale, right? Now,
Okay.
if the whole thing is accelerating downwards with 2 meter per second square, what do you expect? The mg is bigger or the tension is bigger? This thing is moving downwards.
Um,
This one or the upward is moving downwards.
down.
Overall, downwards. Which one is bigger? mg or
And
t?
it's moving down, T will be bigger.
When it is moving down in the direction as the mg, it
Mm-hmm.
is moving in the direction of mg, so this mg must be bigger than the t because the
Oh, okay.
mg win. Mg win, that means the t is less. So we start off with the equation. The net force is the mg minus t. Because it's moving downwards, the mg wins. Earlier on, in the first case, it is moving upwards. So this t is upwards. So t will win. Right? So whichever direction it is moving, that direction must have a bigger force. So if it's moving upwards, this upward direction must have a bigger force. In this second case, it is moving downwards, so the mg must be bigger than the t. So we start off with net force is the mg minus the t. mg minus the t. We also know that this net force is according to Newton's second law of motion. The net force is ma. Okay, now I want to make the t the subject of the formula. This is a negative t. Negative t, you have to move to the other side. It become positive t. The ma, you have to move to the right hand side. Becomes negative ma. So what we have is the tension, the t equals to mg minus ma. And how
Okay.
much is the mg? Mg is given the weight of the fish, 40 newtons. How much is the ma? M is 4.08. We have calculated earlier. And the
Okay.
acceleration downwards is 2. It's given to us, the acceleration downward is 2. So 40 minus 8 is around 31.8 newtons. So when it is moving downwards, the weight actually helps. So the tension will be less. When it is moving upwards, the tension has to overcome the weight. So it has to be more. Okay. Any questions so far for these two cases?
No question, sir.
No question. No question, then we look at the last case. The last case, they say the cable of the elevator breaks. What does the scale reading? What is the reading on the scale? Okay, right. So when the scale, when this it's not the scale, sorry, when the cable that is holding this one, we are talking about this cable here, this cable here, when this cable is cut or is broken, then it will be a free fall. The whole thing will fall down freely due to gravity. And if it is free fall, the acceleration will be g. This one. So the acceleration, the overall is g. Now, the other cases earlier on, there is no free fall. Acceleration is 2 meter per second. So in the first case also, the acceleration is 2 meter per second. It is given. Now the acceleration is not given, but the cable is cut. If the cable is cut, the whole container here, the whole the box here will fall down with an acceleration of g, because we know it is going to be a free fall. So we are going to form the equation once more. Since it is moving downwards, we use mg minus t or t minus mg. Which one? The g is downwards and the force acting downward is mg. So we use which force minus which force to get the net force. This is also the case of moving downwards. So if moving downwards, who wins? If it's moving downwards, the mg wins. So mg minus t. So in this case, it is free fall downwards. Who wins? The mg will win, right? So we say that the net force is equals to mg minus t. mg minus t. Oh, the net force is actually equals to ma. This net force here is actually ma. But because it is free fall, this one is actually a. No? This is actually a. But because we know it's free fall, it is falling with an acceleration of g. So the a here I replace with g. Okay. So as a result, the tension here is mg minus mg. So the tension becomes 0.
Yeah,
So when it is experiencing free fall, actually the balance, the scale here is falling together with the fish. They are moving at the same time. The two of them, they are moving together. So actually it is neither the balance is pulling the fish, nor the fish is pulling the balance, because both of them are experiencing free fall. Both of them, they are falling together at the same rate g. So there's only a contact between them. They are touching each other, but they are not exerting a force on each other. Okay, so this is the case of free fall.
So
When
no, I use toilet for a while.